All right. So more building blocks. I only broke these up so the videos would be shorter. So we'll talk about demodulators, mixers, and filters. For AM demodulation, in other words, we have our amplitude modulator over here on the left-hand side. So we've got our carrier and a modulating signal we call a baseband signal into this essentially multi-frequency multiplier. If we take that and we feed it into what we call an envelope detector, which is the simplest form of AM, we just run it through a diode to rectify the positive portion of the signal. Because if you look at that envelope we saw before, it's positive and negative. It's one's a duplicate of the other. And then we just low pass filter it, and we will recover the modulating signal. And when I ran that simulation, this is the modulator. This is what we got out from the modulator. And this is what we recovered after the low pass filter and the diode detector.
So just for my basic understanding, the purpose of demodulation is simply extraction of the carrier message itself.
Right. It's to unmodulate.
Gotcha. Right.
And for AM, it's fairly simple. Now, single sideband, there's different ways to do it. This is what you would normally see in a modern radio, whether it's an SDR or not. If it's a software-defined radio, all this is going to be done essentially in software and some hardware. But it can still be done in the analog world, and probably most of the modern radios before SDR use this technique where we have what we call the I and the Q signals. So we have a signal coming in, and this would normally be your intermediate frequency. And you feed it into two different mixers, and they're being modulated with a variable frequency oscillator, which is what you're tuning it to, in phase and 90 degrees out of phase. So you generate the in phase signal, which is the I, and the Q or the quadrature signal, which is 90 degrees out of phase, called quadrature because there's 4 quads in a cycle or a circle of 90 degrees. You low pass filter those and then do the process again with a different oscillator. This is the, what do we call that? Beat frequency oscillator. You used to call it the beat frequency. I don't know. Don't really call it that.
Basically, it's your intermediate frequency, whatever your filters were.
Right. And then you can get out the normal and the inverted signal. So kind of the pictures here is you've got upper and lower sidebands relative to, I guess that's FLO1. I'm not sure. No, that's FLO1. Okay. But if you notice, okay, like the lower sidebands, they're mirror images of one another, and the uppers are mirror images. When when we do all that combining, okay, we get rid of the lower, and when you put in the beat frequency oscillator, you offset it back to where it should be frequency wise. Whoop. Damn. I can't go up any higher. And you wind up with both the normal and the inverted. In the normal case, you've got the mirror images of the upper sideband. In the inverted case, you got the mirror images, but they're frequency inverted. I'm not sure what you do with the inverted case. Why they even bother.
It just happens to be there.
Well, but they didn't have to add this extra circuit.
That's true, you don't have to. They're just showing
But
you upper
yeah.
sideband and lower sideband.
Okay. And invert them. And invert them.
If it's inverted, it's going the opposite direction, right?
Because that comes up in one of the satellite things,
I didn't know that.
transponder. And it's on the test.
Oh, I didn't know that.
Inverted. I can't remember the question, but anyway. All right. Let's see what we got here.
Which test are you referring? Just out of curiosity, Robert, which
Not
test
the
do you
tech.
see that discussion on? On what?
Not the technician. It's
I think that's on the extra.
I think it's the extra.
Okay.
All right. So some way. This one, and
It gained a lot of advantage with sideband because effective power is much higher because the bandwidth is narrower. Both.
yeah. I think this one is trying to show kind of what the waveform for a single sideband signal looks like. I haven't had much luck in actually finding what I think is a decent one, probably because it's very hard to capture since there's no reference. There's no carrier to lock on if you want to look at it with an oscilloscope. So it's not an easy thing to see. This is sort of what it might look like, where this is the, I guess, the modulating signal, and that's the waveform. Okay, so next we have a frequency modulation and how you demodulate it. It used to be you would use what's called an FM discriminator in the tube days. I guess some of the solid state stuff still does a discriminator. You have to use some reactants.
Still called a discriminator.
Well,
But never.
not when it's synchronous detection like this, where you're using a phase lock loop.
Never did.
Oh, phase lock loops are cool. And it's a single chip, an integrated circuit.
When I did it, they didn't have those chips.
Well, they didn't have one I started either. So in this case, with this synchronous, what they call synchronous, you've got your signal coming in, and this symbol represents what they call a phase detector, and you're feeding it with the output of a voltage controlled oscillator. And it's going to output an error signal, which is proportional to the difference in frequency or phase of these two inputs. So as that error signal increases, you filter it to get kind of the average of it, get all the high frequency spikes out. And then you use that to control the frequency of the voltage controlled oscillator. So if the error signal is telling you that the oscillator is lower frequency than the reference, it's going to increase, the error signal is going to increase the frequency of the oscillator until that error signal goes essentially to zero. And at that point, we call it phase locked. So as this input signal, which is varying frequency, as that frequency varies, it's going to, again, generate an error signal, which is going to cause the circuit to track it. But that error signal is proportional to the frequency change. So what you're going to see on the output is the modulating signal that's causing the frequency change of the carrier. And this is just showing the modulation part of it, where our, or in this case, the demodulation, the result of detecting that frequency change with a circuit like that. The other big thing is a mixer that we kind of need to do a lot of this modulation and demodulation. There are passive and active components that can be used as mixers. We have unbalanced mixers, which is basically a nonlinear device, could be a diode, a transistor, base emitter junction, things like that. And that gives you all of the components when you multiply the frequencies, not only the, in essence, carrier and the sidebands, but multiples of them. If it's a balanced mixer, and we have double balanced, I'm not sure what a triple balanced is. It's essentially a diode ring, like a bridge rectifier. That's balanced between some center tap transformers. And the main advantage is it only gives you the sidebands. You do not get the carrier. So it is a simple way to do suppressed carrier. This is a typical balanced mixer. You actually can buy these in a, see, who was it? Is it not Micro? Can't remember the name now. Is it not Micro Circuits, is it? Used to sell all this stuff in little modules. I think they still do.
I think that, I don't know.
Anyway, I mean, you can buy a package that has this balanced mixer in it, or double balanced mixer. I simulated this in Circuit Lab. So we got a 50 kilohertz signal coming in, and a local oscillator of a 1 kilohertz signal. And what we get out, okay, is this nice looking waveform. Okay, so mixers can be used to do what we call up conversion and down conversion. So if we have this RF frequency and we feed it into a mixer with a local oscillator that's a higher frequency, we're going to get an intermediate frequency out, which is at a lower frequency. We call that down conversion. If, in this case, why are they showing two?
Up conversion.
I know, but why?
Local oscillators, high frequency, and you're putting in the IF signal.
All right, we're feeding the IF and the local oscillator to get these two RFs out. above and on either side, like sidebands. So this
Like
is
a
sort of,
super heterodyne receiver
yes.
and a transmitter.
I was just trying to see if there was any relative information on these. Because it's not my slide. But it looks nice,
You know, you're taking your RF in,
right?
you have your local oscillator. It
Right,
takes it down to the intermediate frequency.
right. Which
The
is
other
kind of
side, you're
standard.
taking your and going up in frequency. You're raising the frequency up.
All right. This is what you normally do in the front end of a heterodyne receiver.
Yeah.
Okay, in the next piece, we need filters. And they come in low pass, high pass, and band reject, which is sort of the inverse of a band pass. Probably use low pass filters more than the rest. And it will pass frequencies below what we call the cutoff frequency and attenuate any frequencies above the cutoff frequency. Whereas a high pass is kind of the opposite. It passes frequencies above the cutoff and attenuates frequencies below. The band pass is kind of putting a high pass and low pass together so that you only pass frequencies between the upper and lower cutoff frequency. And you reject or attenuate any signals that are outside of that band. In the band reject, it's kind of like the reciprocal of it. You pass all signals above and below that band you're trying to reject. A lot of times we call this a notch filter, where you want to block a specific noise source.
It's usually in the audio frequency range.
And the cutoff frequency is what we call the 3 dB or half power point, where the output of, say, the low pass filter is 3 dB down or half of the input. Here's a typical, probably the simplest low pass filter, which is just a resistor and a capacitor. We're feeding with 10 kilohertz and you can see that at the cutoff frequency, which I didn't write down what it was, but it's in the looks like it starts about 30 megahertz. Probably 3 dB down here at about 100. And this is just a plot of the phase shift, because in these filters, you're going to get change in phase from whether it's in the pass band or out of the pass band. The same thing as a high pass filter, all you do is switch the capacitor and resistor so that at higher frequencies, this capacitor has less and less reactance or opposition to current flow. So you see more of the input, whereas at low frequencies, it's essentially blocking the input. And the same thing here, right around there would be the cutoff frequency. And again, you see the phase shift. And if we compare them, see, this is going from 90 to 0 as you go up in frequency. This is going, in the low pass, it's going from 0 to minus 90. And when we do a band pass, which is in essence a low pass and a high pass together with separate cutoff frequencies, an upper and a lower, and we see the pass band is this nice yellow curve. And we also see the phase shift going from 90 through 0 to minus 90. So it's the same thing you get with the high pass and the low pass when they're put together. So you get a complete 180-degree phase shift through this.
Both just use inductors and resistors, just to reverse them.
Yeah, but they don't usually do that.
Because they're
Simple
more
ones.
expensive to use
Yeah,
that way.
right. This is a band pass showing what we call a multi-pole. I don't know if this is might be a Chebyshev. There's names for these different multi-pole filters. There's Butterworth and Chebyshev and a couple more that I can't recall off the top of my head. And as you add more and more stages, you can see that these skirts get steeper and steeper around this pass band. The downside is with a passive filter like this, you get a lot of what we call insertion loss. So even in the pass band, you can see that the difference between the 0 dB line, which would be the same as the input, we have some loss there, which I can't really tell from this chart, but it would be a few dB. This is just showing op amps again. And again, this works great at low frequencies where you can do an active filter and create a band pass or high pass or low pass. And in these cases, I guess that's a 2-pole. You can add some gain in the circuit to make up for the insertion loss, or actually even have a positive gain through the filter. And you can see the outputs here in the bandpass filter. This is a pretty narrow one. And the high pass filter and the low pass filter. And it's very easy to cascade these to get multiple stages and increase the skirts. You'd get 6 dB per decade.
Computer's not plugged in.
Better do that. So I didn't forget to record. I just forgot to plug it in the other end. Okay.
Yeah, it shows your recording.
Okay. Any questions on those?
Nope.